Good morning, everybody. Welcome to the 35th monthly global online seminar in biodiversity informatics. We have today with us Professor Michael Grabchuk, and he'll be speaking about what is the probability of discovering a new species. For upcoming events, just so you know, on 30th October, we will have a seminar from Fabricio Villalobos. He'll be talking about phylogenetic conservatism of Grinnellian ecological niches. So put that on your calendar. It'll be the usual time of 9 a.m. Chicago time, and I believe that's still GMT -5 for those of you who are tuning in from around the world. So back to the present. Michael Grabchuk is Associate Professor in the Department of Mathematics and Statistics at the University of North Carolina, Charlotte. And today he'll give us a talk entitled, "What is the probability of discovering a new species, Turing's formula and diversity indices?" So I'm going to turn this over to Michael. And Michael, thank you for your morning.
Well, thank you for the introduction, and thank you for inviting me to give a talk here. So as you said in the introduction, I'm at the Department of Mathematics and Statistics. My background is in probability and statistics, not in ecology, but I'm interested in applications to certain things in ecology, and that's kind of why I'm excited to give a talk here to ecologists to see first, whether my work is useful for ecology, and second, to get some feedback, perhaps directions that I could go in and things of that nature. So that's kind of the goal with this talk, just to present some of the things I've been working on along with my collaborators, and to see what ecologists think of it. So let's get started with a talk. So okay, so is the talk up now?
Yes, you're great.
Okay, great. So here's the talk. So as it's called, "What is the probability of discovering a new species? Turing's formula and diversity indices." And the talk will be in three parts. First, I'll talk about the estimation of the missing mass. Missing mass is just what we in probability call the probability of discovering a new species. Then I'll talk a little bit about Simpson's diversity indices, and then I'll talk about some more general diversity indices and how to estimate them. Now, throughout this talk, if you have any questions, please email this address here, biodivtraining@gmail.com. Before I get started, I should say, due to some technical issues, I'm not able to maximize the screen any further than this, but hopefully everyone can see the screen as it is this way. So let's get started with part one, the estimation of the missing mass. This is joint work with my colleague at UNCC, Zizan. Now, before I get into formally defining the missing mass and talking about how to estimate it, I want to start with just a very simple, very basic example to kind of get on this, so that we're all on the same page in terms of what kinds of problems we're thinking about. So here's a simple example. Consider the bird population in a particular location. It's comprised of some species. Let's call these A1, A2, and so forth. Now, corresponding to each species is its relative proportion in the population. So P1 is the proportion of birds of species A1, P2 is the proportion of birds of species A2, and so forth. Now, of course, in practice, these proportions are unknown. So the only way we're going to know what they are is to get some data. So let's say we get a random sample of size, say, 2,000. So we've observed 2,000 birds in this population. And perhaps we've seen 300 birds of species 1, 200 birds of species 2, and so forth. With this information, we can now estimate the proportions. So for instance, there's 300 birds of species 1, so 300 divided by 2,000 is 0.15. So we can estimate the proportion of birds of species A1 by p hat 1 is, which is 0.15. Similarly, there's 200 birds of species A2, so we can estimate the proportion of birds from species A2 as 200 divided by 2,000, or 0.1, and so forth. We can estimate all of these probabilities in this way. And so we can answer a lot of questions once we know these probabilities or proportions. For instance, question 1, what is the probability that the next observation will be of species A1? Well, a good estimate for that, or a good answer to that, is the proportion of birds of species A1, which we can estimate very well by p hat 1, which we saw is 0.15. But there's other questions of a similar type, but that we cannot answer just knowing these proportions. So for instance, what is the probability that the next observation will be of a species that we have not observed before? Now, if we apply the same methodology that we used to answer question 1, we'd say, well, we saw 0 birds from any of these species. 0 divided by 2,000 is 0. So we would estimate this probability as 0, which I don't think is a very reasonable estimate. A more useful answer is provided by Turing's formula. And Turing's formula says that we can estimate this probability very well by looking at the number of species occurring exactly once in the sample divided by n, the sample size. So this is claimed to be a good estimator for the probability that the next observation will be of a species not observed before. So before saying more about this formula, I just want to provide some intuition for it by considering 2 extreme situations. So for instance, consider the case where all of the observations are from totally different species. So we saw 2,000 birds, and each one of them is from its own species, so we saw 2,000 different species. In this case, the number of species occurring exactly once in the sample is, well, all 2,000 of them. So Turing's formula reduces to n over n, or 1. And I think intuitively, if we've seen so many 2,000 birds, and each one of them has been from a different species, it seems reasonable to say that the probability that the next bird will be from a new species is close to 1. Probably we wouldn't want to say that it's exactly 1, but it seems, I think, intuitively reasonable that it should be close to 1. And Turing's formula, in that sense, estimates this to be close to that by saying that it is 1. On the other hand, now let's consider the opposite extreme situation, where all observations are from a few very abundant species. Perhaps there's just 2 species. Maybe we saw 1,000 birds of species 1, 1,000 birds of species 2, and that's it. In this case, we don't have any birds from a species occurring exactly once in the sample, and so Turing's formula reduces to 0 divided by n, or 0. And I think, again, in this case, if you've seen 2,000 birds but only 2 species, and both pretty abundant species, then the chance that the next time we'll see a new species probably isn't quite 0, but very close to 0, and so 0 seems like a reasonable estimator. So that's at least to give some intuition as to what Turing's formula is telling us. Now, before we get going, I need to define some notation that I'll use throughout this talk. So, so let A be an at most countable alphabet, and basically these A1, A2, and so forth, these represent the species in the population, and corresponding to each species is a probability, P sub A, corresponding to its relative proportion in the population. So P sub A is the proportion of species A in the population. Since the probabilities are unknown, we must estimate them from data. So our data is going to be a random sample x1 through xn, where x1 is the species of the first bird we observe, x2 is the species of the second bird we observe, all the way until xn, which is the species of the nth bird that we observe. Now, L sub n of A is the sample counts of species A. So L sub n of A is the number of birds in our sample that have species A. And that can be used to estimate the probability as P hat A equals L sub n of A divided by n. That's the usual standard estimator for that probability. And perhaps the most important notation we'll come back to the most are these KRNs, which is the number of species observed exactly R times in the sample. So now when R equals 0, that's the number of species that aren't observed in the sample at all. That's something that we don't know. We cannot, we don't know what K0n is, because unless we know the number of species in the population, and we're not assuming that we know that. So so K0n we don't know from just our sample, but all of the other KRNs we know, right? K1n is a number of species observed exactly once in the sample. That's certainly something that we know, and so forth for the rest of them. So that's something that is known once we have our data. Okay, so now we can formally define the missing mass. So the missing mass is the total probability associated with species not covered in the sample, and it's given by this mathematical formula. So it's the sum over all species A in our ecosystem, P sub A, the proportion of birds of species A, times this indicator telling us we're only summing up those species that we have not observed in our sample. So what this represents, of course, is exactly the probability of discovering a new species. But again, in probability theory, we like to call this object the missing mass. And this is something that we want to estimate. Now, it's a kind of a strange object to estimate. In statistics, we think of things that are parameters and things that are statistics. And this is neither a parameter nor a statistic. Parameters are things from the population that we don't know. So the P sub A's are parameters because we don't know them. Statistics are functions of the data, and since we have this thing here that depends on our sample, this is kind of like a statistic. It depends on the sample, but it's not. But because it both depends on the sample and on the unknown probabilities, we wouldn't call it a parameter nor a statistic. So it's kind of a strange object for statisticians to look at because it behaves a little bit differently than what we're used to. For instance, different sample, we want to estimate it because it depends on things we don't know. And yet, at the same time, it depends on the sample, and different samples will give us different missing masses. As we said, a good estimator for the missing mass is provided by Turing's formula, which is the number of species occurring exactly once in the sample, divided by n, the sample size. So number of species occurring exactly once in the sample. Now we have this notation K1n, which means exactly that. So this formula was first introduced in Good 1953, where the results were largely credited to Alan Turing. In fact, this formula was first developed by Alan Turing in the 1940s when Good was his statistical assistant, and they were both working to help decode the Enigma code. And so this result was highly classified for a very long time, and something like 10 years later, when Good sat down to write this paper, he said in the paper that Alan Turing had provided a very good intuitive explanation for what this formula means, using something like either cards or balls and urns, but he no longer remembered Turing's motivation for this formula. So we don't know how Turing came up with this formula, but certainly to analyze an estimator, we can always use the methods and procedures that we use in statistics to figure out how good an estimator is. So one simple thing we could look at is what's the bias of the estimator, and it's not difficult to derive that the bias of Turing's formula is of this form. Notice here we have n, where n is the sample size. So essentially the bias decays exponentially fast, because this is, of course, something raised to the power n. So for large n, the bias is quite small. Another thing we could look at is consistency. Consistency is whether the estimator approaches what it's trying to estimate. So it would be asking, does Turing's formula approach the missing mass? But here we have kind of a strange situation because both Turing's formula and the missing mass depend on the data that we have, and different samples give us different values for these things. So we can't really talk about Turing's formula approaching the missing mass because the missing mass itself is changing as the sample size changes. But we can definitely say that the difference between Turing's formula and the missing mass goes to 0. So this seems like a nice result, but then if we think a little bit more into it, we can see that both the missing mass and Turing's formula go to 0 as n goes to infinity. So in other words, what we're really saying is that something goes to 0 minus something else going to 0 goes to 0. And in that sense, this is not a very interesting result that Turing's formula minus the missing mass goes to 0. So a more meaningful way to think about this was given in Ohanesi Nandala 2012, where it is suggested that it is more meaningful to consider consistency in terms of relative error. So we look at the difference between Turing's formula and the missing mass divided by the missing mass. Now, if this difference goes to 0 faster than the missing mass goes to 0, now we actually have a useful estimator. And, well, unfortunately, this does not hold for all distributions. But Benamou et al. 2017 gave sufficient conditions for when it does hold. It holds for quite a few different classes of distributions. Now, in this talk, or at least this part of the talk, I want to talk about a slightly different problem than just estimation. Estimation is just, does the estimator get close to what it's trying to estimate? But I want to say more. Can we use this estimator to somehow construct confidence intervals or hypothesis tests? To do that, we need more than just to know that we're doing a good job estimating things, but we need to know how, what kind of distribution we're approaching, right? How what kind of distributional properties we have in the asymptotics, and not just if we're getting close to what we're trying to estimate. So, so what we'll consider is under what conditions do we have asymptotic normality? Now, the question of asymptotic normality for Turing's formula goes back probably to the paper of ST 1983. And since then, a number of papers have been written looking at this problem, a lot of them by my collaborator, Zhi Zan. So I will talk about our some of the results in our newest paper on this topic, which was just recently published. And so let me just give the main theorem. So under certain conditions, which aren't very complicated to write down, but I just don't want to clutter up the slide with some technical, too much technical notation. But basically, under certain conditions, the difference between Turing's formula and the missing mass divided by the missing mass, this relative error, scaled appropriately, converges to a standard normal distribution. And notice everything here in how it's being scaled are things that we can get from our sample, right? It all depends on these K1s and K2s. So K1, again, to remind everyone, is the number of species observed exactly once in the sample, and K2 is the number of species observed exactly twice in the sample. So these are things that we know and we can estimate, and then we can use this asymptotic normality to create confidence intervals or to do hypothesis tests. So for instance, if you're interested in confidence intervals, we can transform this into this confidence interval. So a 1 minus alpha times 100% confidence interval for the missing mass can be given this way, again, in terms of the K1s and K2s. And then, of course, we have this usual term here, Z alpha over 2, which is the quantile of the standard normal distribution. Specifically, if Z is a random variable with a standard normal distribution, the probability that Z is bigger than Z alpha over 2 should be alpha over 2. So with that, we get this confidence interval. Now, of course, we have some assumptions for when asymptotic normality holds. And we don't know in practice if those assumptions are really going to hold for our data set or not. But as a reasonable rule of thumb, we can consider, we look at K1 divided by 2 times K2. If this is not very close to 0, then the confidence interval should be should work well. Okay. Now, as a corollary to the theorem, under the conditions of the theorem, we also get asymptotic. We also get consistency in terms of relative error because, well, asymptotic normality generally implies consistency as well. And it appears that our conditions are different from the ones given in Benamou et al. Remember, Benamou et al. Gave some conditions for when this holds. Our conditions seem to be different. It's not clear how different they are. A lot of distributions seem to satisfy both sets of conditions, but at least they appear to be different ones. Okay, so one application of this is how many observations are we going to see from a new species? So that's a question we might be interested in. So assume that we have a sample of size n, and we use it to estimate the missing mass by Turing's formula. So we have one sample of size n, and we use that to estimate the missing mass. Now we want to take a second sample of size m, and we want to ask, how many observations from new species do we expect to see? Well, this can be estimated by m times Turing's formula. Now, we should be careful in terms of what this means. I'm not saying that we expect to see m times Turing's formula a number of new species. We're not saying that this corresponds to a number of new species at all, just number of observations coming from new species. So for instance, if this number m times t is 10, we don't know if that says that we expect 10 observations from the same new species, or 10 observations each from a different new species. So we're not talking about estimating the number of new species we'll see, just the number of observations coming from a new species. Okay, now the results that I've discussed so far can be generalized to something more general called the occupancy problem. And so now let R be a sum number between 0 and n minus 1, where n is our sample size. And we define the occupancy probabilities in this way as the sum of the probabilities associated with species that have been observed exactly R times. Now, if R is 0, this is exactly the missing mass, or the probability of observing a new species. But we can ask we can consider any R between 0 and n minus 1. And in this case, we can estimate MRN by what is called the rth order Turing's formula, which is given this way in terms of, so it's some constant depending on R and N. And the main thing here is this KR plus 1, where KR plus 1 is, of course, the number of species observed that we see exactly R plus 1 times in the sample. So this exactly reduces to Turing's formula when R equals 0. And pretty much all of the results that I've discussed here can be extended to this case. So we get asymptotic normality, consistency and relative error. All of these results can be done for any of these MRNs. But I think in many ways, the missing mass is the most interesting and most important one. So that's the one I focused on here. But the results in our paper consider this more general situation. OK. So now let me move on to the second part of this talk, which is about estimating Simpson's diversity indices. This is joint work, again, with my colleague at UNCC, Zhi Zan, as well as Eric Marcon and Gabriel Lang at Agro Paris Tech. And if you have any questions, again, please email them at this email address. And after the talk, I'll be happy to answer any questions. Okay, so so let's get started talking about Simpson's index. So in 1949, Simpson published a paper which introduced a diversity index zeta 1 in this form. So this is sometimes called Simpson's index or the Gini-Simpson index. Actually, when we say Simpson's index, usually we mean a slight reparametrization of this object, and Gini-Simpson refers to this object specifically. But I'll just say Simpson's index for talking about zeta 1. Now, zeta 1 actually is exactly the expected value of the missing mass based on one observation. So in this sense, this very closely relates to the first part. In the first part, we were talking about estimating the missing mass. And now we're basically talking about estimating the expected value of the missing mass. Well, in this case, based on one observation, but we'll talk about more general situations in a few slides. So the idea of thinking of this as a diversity index is that the larger zeta 1 is, the more diverse we can think that population is. So we have some population, and it has some proportions for its species. And then this object is just a way of summarizing those proportions in a way that the larger this is, we can think of the ecosystem as being more diverse. And if this is smaller, then we can think of the ecosystem as being less diverse. But of course, in practice, we don't know these probabilities P sub A. They must be estimated from from data. And a simple estimator for this object is what's called the plug-in estimator. We just estimate the probabilities, plug them into the formula, and we have an estimate for Simpson's index. So this is a simple estimator, but it turns out that it is a biased estimator. And Simpson, in the same 1949 paper, suggested that an unbiased estimator, given this form, which I'll call Z1, is a better estimator because now this estimator is going to be unbiased. So notice it's basically just the plug-in estimator times n over n minus 1 to get rid of the bias. Now, Zhang and Zhao 2010 introduced a more general class of indices, which they called generalized Simpson's indices. And they are given in this way: zeta v for any v in the integers, the natural numbers. So v is 1, 2, 3, and so forth. And now it's given as the sum over all species A in our ecosystem, p sub A times 1 minus p sub A raised to the power v. So Simpson's index raises to the power 1. Generalized Simpson's indices raise to any natural number v. And one way to think about these indices is they kind of weight probabilities differently, right? So if p sub A is very close to 1, then 1 minus p sub A raised to v, if v is fairly large, is going to be a very small number. Whereas if p sub A is a small number, 1 minus the small number is pretty large, and then raised to the power v, it gets smaller, but not as much. And so in that sense, the larger v is, the more weight is placed, or the more relative weight is placed on probabilities that are smaller. So that's one way to think about what this formula means. And another thing is, this is exactly the expected value of the missing mass based on v observations. Okay, an important and interesting fact about this is that the collection of all zeta v's, so if we knew all of the zeta v's for n equal, I put n here, but that's a typo. This should be for v equals 1, 2, 3, and so forth. If we knew all of the zeta v's, then that uniquely determines the probabilities p1, p2, and so forth. So knowing the generalized Simpson's indices is basically equivalent to knowing the probabilities. Okay, so in that Zhang and Zhao paper, they showed that an unbiased estimator of generalized Simpson's indices of any order v from 1 to n minus 1. So if we want to estimate generalized Simpson's index of order less or equal to n minus 1, where n, of course, is the sample size, then they provide this nice estimator for doing so. It may look a little bit complicated, but it's nice in the sense that it's pretty simple to program this into a computer, and the computer can pretty quickly and efficiently evaluate this estimator. If v equals 1, then this reduces exactly to the estimator of Simpson 1949. And an interesting fact is, if v equals n minus 1, then Zn minus 1, the estimator of that generalized Simpson's index, exactly reduces to Turing's formula. So just like Turing's formula is a good estimate for the missing mass, it's a good estimate for the expected value of the missing mass based on n observations. Okay, so a number of properties of these objects have been studied in some of our papers. So, for instance, ZV is a UMVUE for zeta v. So that means it's the uniformly minimum variance unbiased estimator. So it's an unbiased. So out of all unbiased estimators of zeta v, ZV has the smallest bias. The smallest variance. So out of all unbiased estimators, this estimator has the smallest variance. So in that sense, if you want an unbiased estimator, you really can't do better than ZV. Further, so long as P is not a uniform distribution, we get asymptotic normality. So ZV minus zeta v times some constant goes to a standard normal distribution. Of course, to know exactly what the standard deviation is, we must estimate that. So one way to estimate the standard deviation is to use this formula given here. And this can now be converted to get confidence intervals. So for any v from 1 to n minus 1, we can get an approximate 1 minus alpha times 100% confidence interval by basically taking zv, our estimator, plus or minus something depending on the standard deviation. That comes from this asymptotic normality fact here. So before we go on, let's do an example where we actually apply this confidence interval. So so we're going to consider two 1-hectare plots, number 6 and number 18, of tropical forest in the experimental forest of Paracao, French Guiana. Now, for plot number 6, we get a sample of 641 observations, and for plot 18, we get a sample of 483 observations. Now, what are we observing? We're observing trees with diameter at breast height over 10 centimeters. So these were inventoried for these two plots, and so we saw various numbers for various species. So now we can estimate generalized Simpson's indices for both of these plots for various choices of the v's, and then get confidence intervals for any of those using this formula. So here's a plot of that. So the green line is the green lines correspond to plot 6, and the red lines correspond to plot 18. So the line in the middle is a line plotted through the estimated generalized Simpson's indices for orders from 1 to 250. And then we have a 95% confidence interval around each one of these. One interesting thing to note is that the confidence intervals don't overlap for any of the indices. Well, maybe for this very small one, it's hard to see exactly what's going on here at 1, but it's pretty clear that these profiles behave very differently, and plot 18, even its confidence interval does not at all intersect with the confidence interval for plot 6. So in this sense, it suggests that plot 18 is more diverse than plot 6, at least more diverse in the sense of generalized Simpson's indices. So another thing that, as I understand, ecologists are sometimes interested in looking at is the effective number of species. So the effective number of species is the number of equiprobable species that would yield the same diversity as a given distribution. So for instance, if we observe that, say, generalized Simpson's index, it has a value of 0.5, we can ask, well, we don't know the distribution, perhaps, of species. We don't know how many species there are. But if we had a totally different situation, a totally different ecosystem, one where we had the same all species equiprobable, one where we had a uniform distribution, how many species would have to be in this distribution with a where all species have equal probabilities? How many species do we need to have to get the same generalized Simpson's index getting to be 0.5, just like it was in our observation? So that is called the effective number of species. And with some algebra, we can calculate that for zeta v, generalized Simpson's index of order v, the effective number of species is given by this formula. It's a function of zeta v given in this way. So I use this notation d, zeta, and the order I put here on the left as a kind of a left superscript. Now, of course, since we know how to estimate zeta v, we can always estimate this object by first estimating zeta v with zv and then just plugging it into to the formula to get the effective number of species. And then if we want to get confidence intervals, well, we know how to get confidence intervals for zv. We already saw the formula earlier. And now we can get so if we get a confidence interval LU for zeta v, then a confidence interval for d zeta v is just given by plugging in L here for here. So into the same formula, but instead of zv, we plug in L and U, and this gives us a 1 minus alpha times 100% confidence interval for the effective number of species. So again, coming back to our example with the two plots in the experimental forest of Paracao, French Guiana, we can now do the same thing we did before, but instead of plotting the generalized Simpson's indices, we can plot the estimated effective number of species for the two for the two locations, and get 95% confidence intervals for those. As a picture, I think this is a bit clearer to look at. And again, we see that for the red lines corresponding to plot 18 are above the green lines, and which correspond to plot 6. And in fact, there's not even a little bit of overlap between their confidence intervals, except perhaps right at the very beginning a little bit, but I wouldn't say that says too much. So this suggests that, again, that plot 18 is more diverse than plot 6, at least in the sense of generalized Simpson's indices. Now I want to talk about the problem of comparing two populations. Now, of course, we can always just compare this way, plot things for both populations and see if there's any overlap. But we want to do something a little bit more formal. So let's consider a more formal way of comparing the two populations to see which is more diverse. So we get a random sample of size n1 for the first ecosystem and a sample of size n2 for the second ecosystem, and assume that the samples are independent of each other, which I think is a pretty reasonable assumption if you're looking at samples in two very different locations. Now choose any v less or equal to the minimum of n1 and n2 minus 1. Because remember, we can't estimate generalized Simpson's indices, at least not in an unbiased way, that are bigger than the sample size minus 1. So that's why we can only look at orders of generalized Simpson's index less or equal to this number. I'm also going to make sure that v is less or equal to, so S1 hat the minimum of S1 hat, S2 hat minus 1. So S1 hat is an estimate for the number of species in the first plot, and S hat 2 is an estimate of the number of species in the second plot. Why am I making this restriction? Well, I'll get to that in a few slides, but for now we'll just make this additional restriction. Now we can use the asymptotic normality for the two estimators, the one for zeta v for plot 1 and the one for zeta v for plot 2, and we can create a confidence interval for this difference of zeta v for plot 1 minus zeta v for plot 2, and that's given in this way in terms of the estimated standard deviations for the two plots. And now what we can do is what we did before, plot the order of diversity, and here we'll plot the differences. So now we're not plotting the Simpson's indices, but we are plotting the differences between the Simpson's indices, or our estimates of the Simpson's indices for the two plots. So now we're looking at this difference. So here we plot the difference. So this is the difference along with a 95% confidence interval. This purple line at the bottom is just the line at 0. If this line went through the confidence interval or confidence band that we have here, then we would not be able to say that one species has, one location has more diversity than the other plot. But here, clearly this whole thing is positive, including the whole confidence interval, and 0 is not in the confidence interval at all, suggesting that there's a statistically significant difference in the diversities of these two locations. So specifically what we look here is plot 18 minus plot 6. So again, since this is positive, that suggests that plot 18 is more diverse than plot 6. But when I say more diverse, I'm of course talking about in the sense of generalized Simpson's indices, in the sense that the generalized Simpson's indices for plot 18 are larger than those for plot 6. So that's what we can see from this plot. But you can probably start wondering, well, just having larger generalized Simpson's indices, does that actually mean that that the plot is more diverse? Is a larger generalized Simpson's index really correspond to having a more diverse ecosystem? So, so in general, for a diversity index to be useful, it should satisfy some reasonable axioms. So there's many axioms for what a diversity index should satisfy that appear in the literature. So let me just review a couple of them that I think are relevant here. So let H be now a generic diversity index. I'm not just talking about Generalized Simpson's indices, but just a general diversity index, and what kind of property should it have, and then we'll see if Generalized Simpson's indices have these properties. So first, common property that's assumed is that the diversity index is symmetric in its variable. So if we permute, take a different ordering of these probabilities, we should still get the same value. So in other words, this means that no species has a very specific role to play in the index. So that's the first axiom. Second axiom: this index should be continuous in the inputs. So a very small change in a probability should not lead to a huge change in the index. In particular, that means that if we get one more species added to an ecosystem, but very, very rare species with a very, very small probability, then that should result in a very small change to the diversity index. The third index is called evenness. And so if the number of species in the ecosystem is S, then the most diverse one, the most diverse probabilities that we can have for S species should be when all species are equally likely. In other words, we have a uniform distribution. So for our diversity index, no matter what the probabilities are, it should be upper bounded by the case where the probabilities are all the same. So I think that's a very intuitive thing we'd like to have for something to be called a diversity index. So Generalized Simpson's indices always satisfy the first two axioms of symmetry and continuity. They don't always satisfy evenness. They only satisfy evenness so long as V, the order, is less or equal to S minus 1, where S is the number of species. So this is the reason why earlier when we were talking about, a few slides ago when we were talking about this difference, that's the reason why we wanted to look here and make sure we didn't get V bigger than the sample sizes for the two populations, because this way we wind up with a case where we do have evenness. Now we consider other axioms, and so Generalized Simpson's indices satisfy a few other axioms that are of interest. I didn't put them on the slide, but you could find them in the paper Grabchek, Marcon, Lang, and Zan 2017. Okay, so that's the second part of the talk, and now I want to talk about more general diversity indices. Let's get started with probably the most famous diversity index, which is Shannon's entropy, that was introduced by Shannon in 1948. And it is defined as given here. So it's we have a minus sign, and then we take a sum over all species in the ecosystem, P sub A log P sub A. Of course, we can estimate this with a plug-in estimator. We estimate the probabilities, plug them in here, and we get an estimate. This is a standard estimator that's commonly used, and it's very well studied. So Harris, 1975, considered the bias of the plug-in estimator of H, and found that the bias is of this form. In particular, it decays like 1 over n, where n is the sample size. So it's pretty large bias, or pretty slowly decaying bias. Now, Harris actually isn't the first person to look at the bias. He's probably, as I know, that paper is probably the first one to derive this expansion in a fully rigorous way and with as much detail as given here. But people have been looking at the bias of Shannon's entropy and knew that it was on the order of 1 over n going back to the 1950s. And so going back to a paper in the early 50s by Miller and Maddow, they already knew that the first order term was of this form, and then suggested, well, this means we can make an even better estimator for H hat n by adjusting the bias by adjusting this term. And so if we can estimate S, the number of species, then we can get a lot less bias. So the standard way to estimate number of species is just to see how many were observed in our sample. And then with this new estimator that adjusts the bias a little bit, which is called the Miller-Maddow estimator, now we have bias that decays only on the order of 1 over n squared, so faster decaying bias. But we wanted to see if there's a way to make bias decay even faster, perhaps exponentially fast. And the way to do that is to kind of think of a different way to represent Shannon's entropy. So the classical representation, the one given by Shannon, is in this form, and then both the plug-in estimator and the Miller-Maddow estimator are just ways of plugging in estimated probabilities into this formula. But there's another way to think about entropy. So what we can do is we can take a Taylor expansion of minus logarithm p sub a. And if we do that, we find that entropy can be written in this form. And notice these things here, right? We have sum of v goes from 1 to infinity, 1 over v. And right here, what we have are exactly our generalized Simpson's indices. So now we can what we can do, we know that we can estimate the first n minus 1 of these indices with no bias at all. So we look at the part that can be estimated with no bias, and then here is the tail of everything else that we can't estimate with no bias. So this will estimate, and this will become the bias of our estimator for h. And so we get the estimator for h, h hat z, to be in this form. As a linear combination of the z sub v's, our estimators for the generalized Simpson's indices. And then I won't go through the detailed derivation on the slide, but it's not difficult to see that this means that the bias decays exponentially fast. Here, p min is the smallest probability out of any species in our ecosystem. So this, of course, assumes that S is the number of species is finite, which in applications I assume it probably always is. But of course, the theory can be done even when S is infinite. So in this case, when S is finite, the bias decays exponentially fast. Now, although we know the bias decays exponentially fast, it's nice to get some simulations to get a better feeling for how this works. So let's do some simulations. We'll look at 4 different distributions, 2 with a finite support and 2 with an infinite support. So first, we look at the triangle distribution, which is just basically the probabilities are just k times some normalizing constant for k from 1 to 100. We'll also look at Zipf's distribution, which is 1 over k for k from 1 to 100. And then we look at a distribution on an infinite support, but light-tailed, so the Poisson distribution. And we'll look at a very heavy-tailed distribution on an infinite support, which has power decay and actually, I guess, an infinite variance, which is given here as basically k to the minus 2. And we'll see how things behave. So here's the plot for the biases of the various estimators. So the red line corresponds to what I call the MLE, but that's what we call the plugin. The light green line corresponds to the Miller-Maddow estimator. The blue line corresponds to our estimator, and this black line here corresponds. So we try to adjust the bias of the estimator we proposed, and this is that bias-adjusted estimator. The formula is a little bit complicated, so I don't want to give it here, but it's in the paper if anyone is interested in it. So we see that the plugin is not doing very well. Miller-Maddow and our estimator seem to be quite comparable, at least for these sample sizes, but our estimator does seem to be doing a little bit better. Similar thing we see for Zipf's distribution. For the Poisson distribution, we basically see the similar thing, and the plugin is really not doing very well. I guess the differences between our estimator and Miller-Maddow are perhaps not as clear in this case. And now for the heavy tail distribution, I think this again, the plugin isn't working very well, and I think here we most clearest, we can see the difference in the bias in our proposed estimator versus the Miller-Maddow. And of course, the bias-adjusted version of our estimator is doing very well here. Okay, so that was all about estimating Shannon's entropy, but we can actually apply this for estimating this kind of an approach for estimating lots of different types of diversity indices. So one general class of diversity indices is of this form: sum over all species A in the ecosystem, P sub A times some function f of P sub A, where f is thought of as a measure of rarity. I'm not sure where the indices of this form were first studied, but a very good systematic study of these indices, as well as some other types of indices, is given in Patil and Taili, 1982. So of course, if f is minus logarithm, this just reduces to Shannon's entropy. Now we can do a plug-in estimator for this. Just plug in P sub A hat into the formula for the index if you want to estimate it. But we'll consider a slightly different approach, mimicking what we just discussed in terms of Shannon's entropy. So here is our diversity index that we want to estimate. And if we can take a Taylor expansion of f around 1 with a radius of convergence at least 1, which holds for a lot of situations, then we can again rewrite things as a linear combination of generalized Simpson's diversity indices, where we get these WVs. These are our coefficients for the linear combination, and they come, basically, they're the coefficients from the Taylor expansion of f. So taking Taylor expansion, we can write things as a linear combination of zeta v's, where we know the WVs and we need to estimate the zeta v's. We call such indices linear diversity indices because they're linear in generalized Simpson's indices. And many diversity indices that appear in the literature of this form, of course, the generalized Simpson's indices are. Here, the linear combination is just to take the WVs to be 0, except for a 1 in one location. Shannon's entropy we already discussed. Something that we call Renyi equivalent entropy, that we'll get back to in a few slides, is just we take the sum over all species A, P sub A raised to the power R. And that this turns out to be a very useful and important index, and that can be written in this way as a linear combination of generalized Simpson's indices. Emlin's index, which is kind of a variant of Shannon's index, where instead of logarithm we use the exponential function. Of course, we know the Taylor expansion of the exponential function. And perhaps most interesting, the richness index, which is just the number of species in the ecosystem. The number of species in the ecosystem can actually be written as a linear combination of the generalized Simpson's indices as well. And specifically, if we just add up all the generalized Simpson's indices, that gives us exactly S, the richness index, or number of species. Okay, so a lot of indices are of this form. And of course, we can estimate all such indices in the following way. If our index is a linear combination of generalized Simpson's indices, we know that we can estimate the first n minus 1 of these, and the rest of the terms will be the bias. And this first part we'll estimate by just a linear combination of our estimates of generalized Simpson's index. And now if we have a finite number of species, and if the WVs are bounded, then we get an estimator with exponentially decaying bias. And then we can show asymptotic normality. So under general conditions, we get basically asymptotic normality to hold. And then we can use this to construct confidence intervals. So I want to focus on a specific and important class of diversity indices, which does not actually quite fit into the framework that I discussed, which is Renyi's entropy. And this is a modification or a generalization of Shannon's entropy, and it's defined in this way. Notice in here, this sum is what we earlier called Renyi equivalent entropy. And the reason we called it that is because it's so important for estimating Renyi's entropy, right? Renyi's entropy, basically, the only way it depends on the actual distribution is through this term here that we called Renyi equivalent entropy. So when R is greater than 0 and not equal to 1, Renyi's entropy is given in this way. If we take the limit as R goes to 1, we get exactly Shannon's entropy. So in this sense, Renyi's entropy is a generalization of Shannon's entropy. Of course, this is not a linear diversity index because of the logarithm here. However, as we just discussed, it is just some transformation of HR, which we saw a few slides ago, is a linear diversity index, and our methodology applies to estimating HR. So since we know how to estimate HR by HR sharp, which is our estimator that we just developed, we can estimate HR, the Renyi's entropy, by just taking this formula and plugging into it our estimated version of HR sharp. And then by the delta method, we can show that we still get that so long as we have, so in this case, it's actually easy to say what the assumptions are. If we have a finite number of species and the distribution is not uniform, then we get asymptotic normality for our estimator of Renyi's entropy, where, of course, we need to estimate these sigma hat n's, which there's a formula for doing that, which I'm not giving here. Now, let's go back to our example about the two 1 hectare plots, 6 and 18, of tropical forest in the experimental forest of Peracão, French Guiana. And what we can do is we can just, for various choices of R, we can estimate Renyi's entropy for various choices of R, get a confidence interval for those, and just plot them. So here we look at R's from, I'm not sure exactly where I started. Doesn't quite start at 0, but a little bit. Maybe I think it starts maybe at 0.005, 0.01 or 0.02, something like that, and goes up to 2.0. At 1, we have, of course, Shannon's entropy. And so this is just a plot of our estimated Renyi's entropies for these two plots, along with 95% confidence intervals. And again, using now this different way of measuring diversity using Renyi's entropy, we still see plot 18 is significantly more diverse than plot 6. I should say that this approach, this methodology for estimating diversity indices can be generalized to other related quantities. For instance, Kullback-Leibler divergence, which is a way, kind of an entropy-based way of measuring the distance between two distributions. In this case, the distributions are P sub A and Q sub A. There's a way to do this, to modify our approach to get estimates for Kullback-Leibler divergence that's decay with bias that decays exponentially fast. Similarly, mutual information is a kind of a entropy-based way of measuring dependence between two distributions P and Q. So this can be thought of essentially as kind of similar to correlation, except in some ways it's stronger than correlation, because when we have correlation of 0, that can still mean a lot of dependence, whereas mutual information of 0 actually means that the two are independent. So our approach can be modified for estimating these quantities. And now, of course, our estimators can look a little bit complicated. So we have a package for R, which implements all of our estimators for generalized Simpson's index, for Shannon's entropy, Renyi's entropy, a number of other diversity indices, Kullback-Leibler divergence, and mutual information. So that package is joint work with Li-Juan Chao. Okay, so here are some references for the main papers that this talk is based on. And now, again, if you have any questions, please email them to biodivtraining@gmail.com, and I'll be happy to answer any questions that you have. But thank you for listening to the talk. Okay, so I'm done, and I'm happy to take questions.
Thank you, Michael.
All right, let me exit out of this. Yeah, okay.
We're back to seeing your face.
Yeah, so if you have questions, I'm happy to answer any of them.
Well, actually, from around the table here, we had a couple of questions for you.
Sure.
This one, I guess, from me and from a couple other people.
Mhm.
The question would be, oh gosh. So we have a fire alarm here.
Okay. Should we pause then, or?
It's a test, don't worry.
Okay.
So I'm just going to turn off my microphone from time to time.
Okay.
But the question for you is, how does this work relate to the work of Ann Chow? Which,
yeah, so this work is definitely closely related to things that she works on. So of course, one of the I think main things that she's interested in is estimating the number of species in an ecosystem. So that's a problem that I didn't discuss here, but that's certainly a closely related problem. And then she has a number of ways of estimating entropy. I believe some are modifications of the approach that I discussed here. So I'm not that closely familiar with all of the details of the estimate she uses, but certainly a lot of the things that I discuss are very much in a similar perspective as her work.
It's interesting because Chow's formulas that are used very, very commonly in ecology use the frequency of species observed only once squared, and that the ratio of that number to this number of species observed twice in a sample. And so it seems like that would be using more information than the Turing formula.
Right. So my understanding is that her work starts with Turing's formula, but then goes forward beyond that. And so, I mean, again, I think much of her work in that direction is looking at number of species. That's not the problem that I'm considering here. It's not the problem that Turing's formula directly answers. Turing's formula is talking about the probability of seeing a new species, not the number of species in total. So I think a lot of those formulas are modifications of Turing's formula for estimating number of species, as opposed to estimating the probability of the species. She does have a paper, I think it's probably 1988. It was published something like Chinese Journal of Math, I think it was called, where she actually looks at Turing's formula and derives a modification of Turing's formula which has less bias. So now I haven't considered so that formula definitely works well, and I've done simulations that show that formula really does seem to reduce the bias quite a bit. And of course, there's similar situations, simulations in her paper. So I think the question of whether asymptotic normality holds and other distribution properties of that are very interesting, because it does seem to be a better estimator than just the regular Turing's formula. But I'm not aware of any results about its asymptotic normality or consistency in terms of relative error. I think that's a very interesting question to look at.
Okay, thank you. And another question from one of my students who had to leave for a class, but she was asking, and also
so I'm sorry, I didn't hear what you were saying. Somehow either we got disconnected or for a minute or something. I just heard a little bit of silence for maybe 15 seconds.
Sorry, yeah, you seemed to blink off for just a moment. So one of my students was asking fairly early in your talk, when you were talking about looking at the consistency of your estimators under a number of distributions. The question was which distributions and how many and how diverse empirical distributions.
So you're talking about for Turing's formula?
Yes.
Okay. Now, for asymptotic normality to hold for a fixed distribution, you need some kind of heavy tails. So in the paper, we talk about the various distributions. So you cannot really get things for a finite distribution. On the other hand, if you have a distribution that kind of looks heavy-tailed, but it's not, even if it's on a finite support, when your sample is large but not so large that you start to really see that you're getting that you're getting close to understanding the boundaries of your support, this S-math normality should work quite well. That's, in a sense, that's where I have this formula. Let me go back. To the formula. Where was it? I want to give the confidence intervals. So there's this kind of rule of thumb that I give here that K1 divided by 2K2 should not be very close to 0. And of course, when you have a finite support, eventually both K1 and K2 for large enough samples is going to be 0, and then the rule of thumb will fail. But when the rule of thumb is still okay, I think that the confidence interval should work reasonably well, even if it doesn't quite hold for that distribution asymptotically. But the conditions under which the theorem holds generally require, not generally, always require an infinite support, so infinite number of species, and relatively heavy tails.
Okay. Well, I'm looking at our email account, and I'm not seeing further questions. So I think maybe we'll go ahead and sign off. But Michael, thank you very much for the talk, and that you certainly sparked some discussion around the table here. So thanks very much. And to the broader audience, see you October 30th, when we'll have a talk from Fabricio Villalobos in Jalapa in Mexico. So Michael, thanks once again.
All right. Thank you for inviting me. And if there's any other questions, I'm always happy to discuss these ideas. So thank you.
Great. Thanks again. Have a great day.
You too. Thanks.